All right, today we are doing lecture 11, rational functions. And I wanted to do a couple of examples of rational functions from the classwork and from the tests, but I did just want to start off with a quick definition. So this week we've been talking about rational functions, what they are and how they work. Well, a rational function is just going to be a function of x, where x is the independent variable. So what you're going to have is you're going to have f of x equals a of x on top of the fraction, and then you're going to have b of x on the bottom of the fraction. A of x is called your numerator, b of x is called your denominator, and they are both polynomials with independent variable x. So x is always going to be the variable here. And whatever x value you put in, you're going to get out a y value. But this is only defined if b of x is not equal to 0. Because if b of x was 0, then you would be dividing by 0. Also, you have to assume that a of x and b of x have no common factors. A of x and b of x have no common factors. That's really important, because what you have to do is, for every single question, before you do anything, you have to factor the top as much as you can and factor the bottom as much as you can, even if you can't do it. Because what's going to happen is sometimes factors on the top and the bottom are going to be equal to each other. And in that case, they match up and you can cancel them out. And you can actually reduce that fraction down. It's kind of like how when you were in 3rd grade and they give you 2 over 4 and they say reduce down this fraction. Well, you know that you can take a 2 out of the top and the bottom, right? You can factor the top as 2 times 1. And you can factor the bottom as 2 times 2, since that's just going to give you 4. And then you have the same thing on the top and the bottom, right? You have 2's that match up. So if they match up, you can cancel them out, and then you're left with whatever you have on the top and the bottom. In this case, it would be 1 over 2, 1/2. So that's what a rational function is. And typically, you're going to have something on top, which is a polynomial, like, let's say, x plus 4, and you might have something that has a higher degree on the bottom, like, let's say, we got x squared plus 4x. Well, typically, you wouldn't be able to factor the top because the top is already in simplest form, but you could factor the bottom by taking out an x out of everything. So even though the top has to stay the same, you can't really factor anything out except for a 1, which is pointless anyway. You could actually factor the bottom by taking an x out, and then you'd be left with x plus 4 over x plus 4. So these two factors can cancel out, leaving you with 1 over x. And then you would do all your math on that. Okay. So on the next slide, we're going to be doing problems from the classwork. I'll be doing a couple of them. And we're going to be going through all 5 characteristics. Okay, so by characteristics, what I mean is you're going to be finding 5 things. You're going to be finding, first, if it has any zeros, also known as X-intercepts. Then you're going to be finding all the asymptotes. You're going to have vertical asymptotes. You're going to have horizontal asymptotes. Very rarely, you might even have oblique asymptotes. And then the 5th thing that you want to find is all the holes in the graph, also known as point discontinuities. Point discontinuities, right? We talk about that in our continuity lecture. But those are the 5 things that you need to be aware of. And even if they don't have one of those things, like let's say they don't have oblique asymptotes or they don't have holes or anything like that, you still have to write oblique asymptotes none. You would say there are none of those. So let's try number 1 on the classwork. I've got f of x equals x minus 2 over x minus 3. So for this function, I have something on top, which is called the numerator, and I have something on the bottom, which is called the denominator. Before I get started, I want to make sure that the top is fully factored, and I want to make sure the bottom is fully factored. And since there's nothing really to factor out, we're not going to be able to cancel out anything and make it any simpler than it already is. So we're just going to go ahead and get started. Okay, now for the zeros, what you want to do is you want to set the top equal to 0. So I'm going to take the x minus 2 on top and set it equal to 0. And then you'll have an equation that you can solve for x. So here I can add 2 to both sides. That way I can get rid of the negative 2 on the left side because these are going to cancel out, and I'll be left with x equals 0 plus 2, which is just positive 2. So my 0 is going to be the point 0, 2. 2, 0, sorry. Okay, so for the zeros, those are the x-intercepts, right? That's where the graph is going to cross the x-axis. And all I did was I set the top equal to 0. But now I want to set the bottom equal to 0 so I can find the vertical asymptotes, right? Virginia? Okay, so here I set the bottom equal to 0 and I get x equals 3. That's good. I can stop there. This is not going to be an ordered pair like the last one that we did. This is just going to be the equation of a line. And the line is going to be a vertical line, x equals 3. Okay, horizontal asymptotes. Now, when we do horizontal asymptotes, this is a completely different mindset from what we were doing in the past. In the past, we were setting the top equal to 0 and we were setting the bottom equal to 0. But now we want to think about it totally differently. We want to consider the highest exponent on top, which is degree of a of x. But we also want to consider the highest exponent on the bottom, which would be degree of b of x. And we're just going to compare the two and see if they're equal, or one might be less than the other, and one might be greater than the other. So we're going to take a look at that. Okay, so when we look at the degree on the top, we're really looking at the degree of x minus 2, right? So I'm going to write degree of x minus 2. And then when I consider the degree of the bottom, b of x, I'm really considering the degree of x minus 3. X minus 3. And we're just looking at the highest exponent, right? That's what degree means. It literally means the highest exponent. And the highest exponent on the top is going to be 1. Same way with the bottom. The highest exponent is going to be 1. So these two sides are going to be 1, which means they are equal. They are equal. So I'm going to put my equal sign down, and I'm also going to put equals right here and right here, just to make everything look good and neat. So by our rules, when the two sides are equal, we have to consider the leading coefficient. The leading coefficient. What is that, you may ask? Well, these are the big numbers out in front, not the small numbers that are the exponents. We're looking at the leading coefficients. And since they're both assumed to be 1, we're going to get y equals their fraction, 1 over 1, which of course is just going to give us y equals 1. That's our horizontal asymptote. What we're doing is we're taking the leading coefficient on top and dividing it by the leading coefficient of the bottom, not the degree. The degree is just for the test. just to test out which rule we're going to use. Okay, oblique asymptotes. These only occur when the top degree is one bigger than the bottom degree. So you're really just asking yourself, is the degree of a of x equal to 1 plus the degree of b of x? That's what you're really trying to consider, because this has to be true for there to be an oblique asymptote. So what's the degree of the top? Well, the highest exponent on the top is 1. The highest exponent on the bottom is also 1. So this side is going to be 1 plus 1, which is 2. So I get 1 is equal to 2. Is that really true? No, it's not. So I'm going to put not equal to. So there is no oblique asymptotes to speak of. Although we will see some later on today, there are no oblique asymptotes for this one, so I just write none. And point discontinuities, the holes, those only occur when you have canceled out factors. And since there are no canceled out factors, we just write none for PD. There's not going to be any actual holes in the graph at all. Okay? There is going to be a discontinuity though, but it's the vertical asymptote that actually does it. So let's go ahead and take this information and let's graph it in Desmos. And as always, I graph the original function that they give me. So when I do go over to Desmos, I'm going to graph x minus 2 over x minus 3. Okay, so let's check it out. All right, so over here on Desmos, I am waiting for, all right, there we go. We are going to graph f of x. F of x was x minus 2 over x minus 3. I'm putting both sides in parentheses, the top and the bottom, just to make sure I don't confuse anything with anything else. Okay? And I get this black function on the screen. That's going to be my rational function. Okay? Now, the first thing I want to do is I want to label the first thing that I found, my zeros. And the 0 is just going to be the point 2 comma 0, right? So I'm going to graph 2 comma 0 on my graph. So I need the ordered pair 2 comma 0. It shows up as a red point down here. That's going to be where it crosses the x-axis. So that's where the 0 comes in. The next thing that I want to do is I want to graph my vertical asymptotes. Remember, my vertical asymptote, I found it when I set the bottom equal to 0. And that's going to be x equals 3 right here. So I'm going to take that and I'm going to graph it on Desmos. X equals 3. I get that blue vertical line that's going down the screen. I'm going to change that to a dotted line so that it's more of a vertical asymptote, so you can see how that gels with the graph. Also, we have horizontal asymptotes. That's going to be the next thing that I'm going to graph. I know that my horizontal asymptote we found out was y equals 1. So I'm going to go back to my graph and I'm going to do y equals 1. And I'm going to make it blue and dot it. There we go. So you can see how the graph very neatly fits into those two quadrants, right? The graph is never actually going to cross those dotted lines because those are the asymptotes. And since there's no obliques, there's no point discontinuities going on, I don't have to worry about graphing any of that either. So that's it. That's pretty much number 1. Hope that helps. Okay, I'm gonna keep that up there for about a minute longer and then we're gonna try number 2. So for all 5 of these questions on the classwork, we're gonna find all 5 characteristics. Let's look at number 2. Okay, so number 2 says g of x equals 1 over x plus 7. So 1 over x plus 7. That's going to be my rational function. There's really nothing I can cancel out here because I can't factor the top, I can't factor the bottom, and the top and the bottom have no factors in common other than 1. But hey, 1 is not really relevant here, so we're not going to worry about factoring anything. The first thing I'm going to do is I'm going to set the top equal to 0. That way I can figure out what my x-intercepts are. When I set the top equal to 0, I get 1 is equal to 0. Okay? Now, is that true? Does that make any sense? No, obviously it doesn't. So there are going to be none. I say none because there are no zeros, no x-intercepts. Now I'm going to set the bottom equal to 0. So that way I can figure out what my vertical asymptotes are going to be. I set x plus 7 equal to 0. So I know I'm probably going to get a vertical asymptote. I'm going to subtract 7 on both sides. So that way I can solve the equation for x. And I get x equals 0 minus 7, which is negative 7. And the 7 and the negative 7 on the left side are going to cancel out. So x equals negative 7. That's going to be my vertical asymptote. Now for horizontal asymptote, I want to consider the degree of the top and the degree of the bottom. So let's do degree of a of x, which is the top polynomial, and let's compare it to the degree of b of x, which is the bottom polynomial. Well, the bottom is obviously going to have a bigger exponent, so I'm going to put a less than symbol just to show you that the bottom is going to be bigger than the top. Now, if this occurs, this is really that first rule for horizontal asymptotes. Our horizontal asymptote is going to automatically be y equals 0. Y equals 0, also known as the x-axis. If you're having trouble finding horizontal asymptotes and you really need help with that, I've got a video that I posted on my channel called Horizontal Asymptotes. It should really help you guys out. Okay, oblique asymptotes. Are there any? No, none. Also, point discontinuities. There are none. There are no canceled out factors, so I don't have to worry about those two. Okay, that is number 2. All right, let's do number 3. Number 3 is h of x equals x squared plus 7x plus 12 all over what? X plus 3. Okay, so for this fraction, I can't factor the bottom, but I can factor the top. How do I do that? I have to multiply to 12. 3 and 4 will do that. So I can factor this as x plus 3 times x plus 4. And those numbers do work because they multiply to 12, but they also add up to the middle number. That's 7. Okay, and the bottom is still x plus 3. That hasn't changed. Now the x plus 3s are going to match up on the top and the bottom. So what that means is I can cancel those two factors out. If you cross out 1 from the top, you have to cross out 1 from the bottom. And you are left with x plus 4. That's pretty much it. So when you graph this, you're actually graphing x plus 4. And whenever you graph x plus 4, you're going to get a line on your screen. But that line is going to have a hole in it because of the canceled out factor. But we'll get to that a little bit later. Okay, the first thing I want to do is I want to find all the zeros. That means I need to set the top equal to 0. Well, we're in luck. We only have a top. When I set x plus 4 equal to 0, what happens? I subtract 4 on both sides, and I get x equals negative 4. X equals -4. So my point is going to be -4, comma 0. We'll see that when we graph it. The vertical asymptotes. Are there any vertical asymptotes? Really? No. And that's because there is no denominator. The denominator is really 1, and that's not equal to 0. So we say there are none. Horizontal asymptotes. Since the top degree is going to be bigger than the bottom degree, notice that we have a 2 up here and we only have a 1 right here. Down here, we have a 1 on top, and then we have just a number on the bottom. So obviously the top degree is going to be bigger than the bottom degree. So there is no horizontal asymptotes. Your oblique asymptotes, you do have an oblique asymptote, right? It's going to be x plus 4. Y equals x plus 4. Are there any point discontinuities? Any point discontinuities? Yes. Remember how we canceled out the x plus 3? We're going to set that equal to 0 and solve for x. So I get x plus 3 is equal to 0. So I'm going to subtract 3 from both sides. And I get x is equal to 0 minus 3, which is -3. So it turns out that I have a point discontinuity at -3. Point discontinuities are always going to show up as holes in the graph. So let's go ahead and graph this. H of x is equal to x squared plus 7x plus 12 on top and x plus 3 on the bottom. So let's do that. Let me get rid of all this. And let's do h of x. Okay, I'm putting all this in parentheses so I don't get it confused with anything else. And we're going to divide it by x plus 3. Put that in parentheses. Yep. And there we have it. That's our function. Notice that it is the line x plus 4 because that is our oblique asymptote. So our oblique asymptote was x plus 4. It's the exact same line. But you do have a point discontinuity. Where is it? X equals -3. So going back to our little chart right here, we know that we're going to find a hole in the graph at x equals -3. When x equals -3, what is our y value? What I'm going to do is I'm going to take this number and I'm going to plug it in to our new function right here. So what happens when x is -3? I get -3 plus 4 because I'm replacing this x with a -3. -3 plus 4, that's going to give you +1. So we get the point -3, comma 1. That's our point discontinuity, -3, comma 1. So I'm going to graph that point, but what I'm going to do is I'm going to graph it as a whole because this point is going to be missing from the graph. So going back here, let's go ahead and graph it. -3, comma 1. It shows up as this blue point right here. And what I'm going to do is I'm going to hold this point down. That way it gives me a whole more bunch of options, right? At the top, this is going to be a closed point. This is going to be an open circle. And this is just going to be an X. And we're not going to bother with that. So now our graph has a hole in it. It has a removable discontinuity at x equals -3. So I can label this as the hole. And that is the graph. Okay. Let me head on back to the slide. I'll leave this up there for a minute longer, and then we'll move on to the last two, 4 and 5. Okay, now you're probably wondering how I got the oblique asymptote. Well, you got to consider the rules for that, right? When we do oblique asymptotes, we want to make sure that the top degree is one more than the bottom degree. That's really what we're looking at for oblique asymptotes. So look at your notes, look at the rule that I wrote down for obliques. It's there, I promise you. Let's look at number 4. Okay, so 4 says f of x is equal to what? X plus 1 squared on top, and we're actually putting x plus 1 in parentheses and squaring it. And then on the bottom, we're going to have the same thing, but it's going to have a different exponent. So same base, different exponent. I'm going to cube it on the bottom. So here I've got a numerator, I've got a denominator. It's technically already factored. Now, if something is squared, that means that I can write it twice. So I'm going to write x plus 1 twice on the top. On the bottom, I have x plus 1 cubed. That means that I can write it out how many times? I can write this out 3 times. So I'm going to do it that way, just to illustrate a point. Okay, so this is the expanded version. What 2 factors are going to match on the top and the bottom? The x plus 1s can cancel out. We also have another pair of x plus 1s. I can cancel those out. So really what I'm left with is nothing on the top, but an x plus 1 at the bottom. So I'm going to have an x plus 1 at the bottom. And since at the top we don't have anything, I'm going to put a placeholder 1 in its spot. Yep. That's going to be our new function. Okay, so let's find our 5 things. We want to find zeros. We can do that by setting the top equal to 0. We do that, it's not true, so there are no zeros. Vertical asymptotes. So we just set the top equal to 0. Now I want to set the bottom equal to 0. Let's do that. We'll find out what x cannot be. I can subtract 1 from both sides. So that way I get x equals 0 minus 1, negative 1. All right, let's compare the degree of the top to the degree on the bottom. Well, the degree on the bottom is obviously bigger. It's going to have the highest exponent. So I get a less than symbol. So we automatically have y equals 0 for our horizontal asymptote. Y equals 0. And do remember that is also called the x-axis, technically, because it's just a horizontal line at 0, right? Okay, oblique asymptotes. Oblique asymptotes. Are there any? No, we don't have to worry about those. Those are very rare. Okay, are there any holes in the graph? Well, x plus 1 does get canceled out twice. So I'm just going to solve this and see what I get. And we'll see what that looks like on the graph. X equals negative 1. Okay, so my x coordinate is going to be x equals negative 1. What will my y coordinate be? Were you able to figure that out? Well, to get my y coordinate, I would have to plug that into my original function. 1 over x plus 1. So let's let x be negative 1 and see what happens. I get 1 over negative 1 plus 1. Negative 1 plus 1 is 0. Whoops, I am dividing by 0. So that means this is kind of crazy, so I'm just going to write none. No point discontinuities. Now there is a point discontinuity there, but it is the vertical asymptote. So it's going to be an infinite discontinuity, not a removable discontinuity like a hole in the graph. So for PDs, we're going to write none. Okay, let's graph this function and see what it looks like. I'm going to hop on over to Desmos, and I'm going to get rid of this stuff, and let's graph f of x. All right, we got x plus 1 squared on top. And then on the bottom, we're going to have x plus 1, but we're going to cube it. There we go. Awesome. I get a green graph. I'm going to change it to black. And there we go. Okay. First of all, did it have any zeros? Did it have any x-intercepts? Well, none, right? So we don't have to worry about the zeros. Next, we're going to move on to the vertical asymptotes. It has one at x equals -1. So I'm going to type in x equals -1, and I get a purple line. I'm going to change it to a blue dotted line so you can see it a little bit better. That vertical asymptote is going to neatly divide the graph in two. Let's take a look at our horizontal asymptotes. We know that our horizontal asymptote is going to be y equals 0, the x-axis. So I'm going to graph y equals 0. Y equals 0. I'm going to change it to a blue dotted line. Good. That is our horizontal asymptote. The graph is never going to cross that. And then the last two things that we wanted to look at, did it have any oblique asymptotes? No, so I don't worry about that. Any holes in the graph? No, there are no holes in the graph. There's a vertical asymptote there anyway, so there wouldn't be a hole to speak of. All right, so that is number 4. I'll leave that up there for a minute, and then we'll move on to the last one. Okay. Let's look at number 5. Now, number 5 is one of these that you can actually factor in the bottom, but not the top. So there are going to be some canceled out factors. Okay, so number 5 is g of x equals x minus 5 on top and on the bottom we're going to have x squared minus 25. X squared minus 25. All right, so let's factor the bottom. The top is going to stay the same. We cannot factor that. You can take a 1 out, but that doesn't matter. We're going to factor the bottom as x minus 5, x plus 5. Since we have difference of squares right here, 25 is a square, I can take the square root of that to get 5, and then we're going to have x minus 5 and x plus 5. And we use the minus and the plus so that we get 0x when we do the FOIL method. So what two factors are going to match up on the top and the bottom? The x minus 5s, right? So when I do that, what am I left with at the top? Nothing, so I'm going to put a 1 at the top. What am I left with at the bottom? Just the x plus 5. So this is going to be the new rational function that I'm going to be doing math on. So let's set the top equal to 0 so that we can find all the zeros. I get 1 equals 0. That's nonsense, so there are no x-intercepts. Vertical asymptotes, we can set the bottom equal to 0. We get x plus 5 equals 0, which is going to give us x equals -5. X equals -5. Good. All right. Horizontal asymptotes, we're going to compare the degree of the top and the degree of the bottom. The bottom is obviously bigger, so I'm going to put a less than symbol. So my horizontal asymptote, if it's a less than, it's going to be y equals 0. And we have two more rules if you get a greater than symbol or if you get an equals to symbol. Okay, oblique asymptotes. The top would have to be bigger anyways, so there's none. And for point discontinuities, we can set the canceled out factors equal to 0. So the factor that we canceled out was x minus 5. So I can set that equal to 0 and solve it for x, just like I did for the vertical asymptotes, except I'm going to get the opposite number because I'm adding 5 to both sides. And I get x equals 0 plus 5. That's going to give me 5. All right. So my ordered pair is going to be 5 comma what? What's my y value going to be? Well, all I've got to do is take the number that I just got and substitute it into the function. Substitute it in right here. And that's going to tell me what my y value is. I'm going to take the x coordinate and I'm going to plug it back into the function to get the y coordinate, because every input has got to have an output, right? Unless you have a discontinuity there, then you wouldn't have an output. But anyways, we're going to find g of 5, g of 5. All I've got to do for this is plug in 5 in our function, and I get 1 over 5 plus 5, which is 1 over 10. 1 over 10. So let me get rid of this question mark, and I'll put in 1/10. 1/10. All right. Good stuff. So the last thing we're going to do is we're going to graph this on Desmos, and we're going to confirm all 5 of these. All right. So let's go on over. Let's get rid of this stuff. And I'm going to type in g of x is equal to x minus 5 divided by x squared minus 25. Good. Okay. So I get the graph. It's obviously got a vertical asymptote somewhere over here. It's got a horizontal asymptote, probably on the x-axis, and I don't think it has any x-intercepts. But let's just go through all 5 really slowly so you can just kind of get a sense of what we're doing. So for the zeros, we don't have any, so we don't have to worry about that. We wrote none for that. Our vertical asymptote is going to be x equals -5. Let's graph that. X equals -5. I'm going to change it to a blue dotted line because it's an asymptote. And asymptotes are always going to be viewed as dotted lines. Okay, so you can see how the graph behaves as it gets closer and closer to -5. It starts shooting up and shooting down in 2 different directions. Let's do horizontal asymptotes now. We know that we got y equals 0, so I'm going to graph that. Type in y equals 0. You'll get that horizontal line on the x-axis. I'm going to change it to a blue dotted line. And then I think the last thing was point discontinuities, right? So we don't have any obliques. We don't have to worry about that. We are going to see what happens when we graph this point 5/110. So let's do that. 5/110. Whoops. There we go. That'll work. Okay, I'm going to make this blue, and then I'm going to make it a hole. So the reason why there's a hole there is because when x is +5, you plug that into the function, you're going to get 0/0. So that's very interesting. So notice what happens when you plug in 5. I'm going to go back to my screen, and we're going to try this again. So we had g of x equals x minus 5 over x squared minus 25. We know that our point discontinuity is going to be at 5/110. 5/110. So my x value is 5. If I plug in 5 to my function and try to figure out what my output is going to be or what my y value is, here's what happens. You're going to replace every single x with a 5. And I'll do that for you. So I'm going to replace every single x with a 5 and see what happens. Okay? So on the top, what's going to happen with that 5 minus 5? That's going to give me 0, right? No problem. On the bottom, what's going to happen? We have 5 squared minus 25. I know that 5 squared is going to give me 25. So really, it's going to be 25 minus 25. So what happens on the bottom? 25 minus 25 is going to give me 0. So I get 0/0, which of course you're dividing by 0, so this is undefined. So it's very clear why you would not have a point where x is 5. You wouldn't have a point for -5 either. In fact, you've got a vertical asymptote right here. So there's not going to be a point to speak of. But you can see how the graph kind of works out and how all the characteristics play a role into how rational functions behave. Okay. If you've got enough and you're ready to go, I'll dismiss you. So class dismissed. If you want to stay after for a few minutes and watch me work over some test questions, you're free to do so. I think I only have to leave at, let's see. Yeah, I got to leave at 9:45. So I got 20 more minutes. We could do some test questions if you like. Now, Monday, I think that I did a video where I did all the odd questions on the test. All the odd questions. I sent you guys an email about that. So after today's lecture, if you want to take a look at that, you can. So I'm going to be looking at the even ones on the test. Okay, let's do some test questions. We'll do number 2 and number 4. How about that? All right. For number 2, I've got g of x equals 1/x. Notice that this is the reciprocal function. We talked about that on the first day. This is the parent function that has vertical asymptotes and horizontal asymptotes. Now for zeros, if we set the top equal to 0, we're going to get 1 equals 0. That's nonsense, so we don't have any x-intercepts. But for vertical asymptotes, if we set the bottom equal to 0, we're going to have x equals 0, and that is already solved for you, so you're good. Moving on to horizontal asymptotes, we know that the degree of the top is going to be less than the degree of the denominator. So we're going to have y equals 0. We don't have any oblique asymptotes, so I'm going to write none. And then for point discontinuities, since we don't have any canceled out factors to speak of, we really don't have any holes in the graph. So that's not going to be a problem. So this is the simplest type of rational function that you'll see. It's a fraction where you have 1 on the top and x on the bottom. Now, obviously, x cannot be 0, because if x really was 0, you would be dividing by 0, which is not defined. So we're going to graph this and see what it looks like. Okay, so I've got g of x is equal to 1 over x. Notice that we have a horizontal asymptote at y equals 0, but we also have a vertical asymptote at x equals 0. And since there are no oblique asymptotes and there are no point discontinuities, I don't have to worry about that. I'm going to make these into dotted lines since they're asymptotes. And yeah, that's number 2. That one was very simple. I liked it. All right, I'll leave this up there for about a minute, and then we'll do number 4, and then I'll get off. All right. So number 4 is going to be a situation where you have 4 factors on top and 3 factors on the bottom. And all 3 of those on the bottom can be canceled out eventually. So let's do that. Okay, so I've got f of x equals x minus 2 to the 4th power. And on the bottom, I have x minus 2 to the 3rd power. I can expand this on the top if I have enough room. I've got to write 4 of these. Good. And then on the bottom, since I have 3 of these, I'm going to write it 3 times. So I'm just expanding this out. That's all I'm doing. Not changing anything to it. So we have 3 pairs that are going to cancel out. This pair, and this pair. And I'm left with x minus 2 on top with a 1 on the bottom. And if I'm dividing by 1, then I'm just going to get x minus 2. Okay, so we're going to set the top equal to 0, and then we're going to set the bottom equal to 0. If we set the top equal to 0, we get x minus 2 equals 0. I'm going to add 2 to both sides so that in the end, we get x equals positive 2. So our ordered pair is going to be 2, 0. All right, vertical asymptotes. If I set this bottom of the fraction equal to 0, I get 1 equals 0. That's not good. So no vertical asymptotes. Horizontal asymptotes, I am comparing the degree of the top to the degree on the bottom. the degree of a of x and the degree of b of x, respectively. The top has a bigger exponent, so we're going to say greater than. So there is no horizontal asymptotes, unfortunately. Our oblique asymptote is going to be y equals x minus 2. Y equals x minus 2, because we're just going to get a line. That's what we got right here, right? For point discontinuities, we're going to take the canceled out factors and set them equal to 0. We canceled out x minus 2 like 3 times, so probably something there, right? I set that equal to 0, and I solve for x. I get x equals positive 2. So for my ordered pair, I'm going to have 2 in the x value, but not sure what the y value is. To find that, I would have to plug that back into our function. So I'll take this and that's not good. I will take this x value and plug it in right here. When I do that, I get 2 minus 2, which is 0. That is going to be the hole in the graph. Okay, so let's graph all this stuff and see what it looks like. So we're going to hop on over to Desmos and we'll see what we get. Okay, f of x equals x minus 2 to the 4th power on top divided by x minus 2 cubed. So x minus 2 cubed. There we go. And we get the line x minus 2, right? That was our oblique asymptote, right? Y equals x minus 2. They're pretty much the same function anyways. So yeah, that's the oblique asymptote. But let's go through all 5 characteristics and see if we can identify them. Going back to our slide, we know that our 0 or our x-intercept is 2, 0. So let's graph that. 2, 0. That point shows up right there. I'm going to make it red. Label that the 0, also known as the x-intercept. So I'll label that right there. Vertical asymptotes, we don't have any. No verticals, so we don't have to worry about that. Horizontal asymptotes, also none, so I'm not going to worry about that. We've already done the oblique asymptotes, so I'm going to skip over that. And then our point discontinuity was 2, 0. That's the hole in the graph. So let's graph that. 2, 0. That should be the hole. It's actually already graphed as the 0. So all I have to do is call it the hole and then hollow out that point. I'll change it to an open circle instead of a closed dot. There we go. So really, does this graph ever cross the x-axis? Does it ever really cross the x-axis? I don't think so. So going back to our little slide right here, when we did the x-intercepts over here, we found out that it was 2, 0, but really it doesn't have any zeros, right? So I'm going to get rid of all this stuff and write none, because there's a hole right there. Simple. Okay, I'll leave this up there for a little bit. So you know what you got to do now. You got to turn in your classwork and your test. If you're still struggling with some of the test questions, watch the video that I posted. It should be listed under Friday. Yep. Okay. I got to go ahead and get off. So you're free to leave. I'm not going to do anything after this, but if you have any questions, you can throw them down in the chat box. And have a great weekend. I will see everybody next Monday.